Hello, my name is Niliana Mumba,
And my name is Andrew Gupta.
and this is our final project for Psych 119. In this project, we modeled a missing person search scenario using Python. Our goal was to simulate the different paths a missing person might have taken and how a rescue team could retrace those paths to try and find them. This kind of simulation can be really helpful in real-life search and rescue operation because it helps visualize the uncertainty and randomness in human movement, especially when there's limited information available. We use a method called random walks to simulate movement. A random walk is a mathematical way of modeling a path made up of series of steps in random direction. In our code, we generate several of these paths to represent where the missing person might have gone after they were last seen. To give our simulation structure, we created a boundary around the search area. We assumed the person was last seen at the center of a 20 by 20 unit grid. The boundary is circular and calculated using the diagonal of the grid. This defines how far the person could have gone realistically. We also incorporated a Monte Carlo simulation, which is a way of running many trials to predict possible outcomes based on randomness. In our case, we ran 10 random walk simulations to see different potential outcomes. Then we used the first 10 of those paths to represent the rescue team's movement, retracing what could have been the missing person's paths. The point of using Monte Carlo here is to represent uncertainty. We don't know exactly where the person is, but by simulating a variety of likely paths, we can get closer to understanding where they might have been and whether a rescue team could be able to find them. Now that I've covered the goal of the project and the core ideas behind it, I'll pass it on to Andrew, who will walk you through how the code actually works in detail.
We start by doing some basic imports, one for the plot, one for randomness, and one for the calculations. Next, we define a few key constants. We set the center as the last known location of the missing person and create a circle with its radius representing a search area based on the diagonal of a 20 by 20 grid. Each random walk step is 1 unit, and each path can go up to 1,000 steps, unless it exits the search area earlier. We then create 10 random walk paths. Each path begins at the center, and with each step, it randomly chooses a direction using trigonometry, cosine, and sine of a random angle. The person moves in that direction, and we record the location. If they move outside the search boundary, the walk stops. Once all 10 paths are generated, we randomly choose one to represent the missing person's actual path, and a random point along it as their final location. Then the first 10 paths are used again, this time representing the rescue crew. These paths simulate the team retracing the possible paths the missing person might have taken. We then create two plots side by side. The first plot, as Nils is showing you, shows all 10 possible paths that the missing person may have taken, the circular boundary, as well as the original center point. The second plot shows only the rescue path that comes close enough to the actual missing person's location within a small threshold we define as tolerance. Finally, we mark the missing person's actual location with a blue square and print a message saying whether the rescue team successfully found them. If a path gets close enough, it's considered a successful rescue. This visual representation helps us better understand how randomness affects search strategies and how simulations like this can be used to model uncertainty in real-life rescue operations.
Thank you for
Thank you
watching
for watching
the presentation.
our presentation. We hope it gives you a better understanding of how random walks and Monte Carlo simulations can be used in modeling complex real-world scenarios like search and rescue.